Yeah, welcome everyone. I'm very happy to see such a good turnout on the Friday morning. I know it's hard to be here early, so thank you for coming. Yeah, I'm presenting this talk, The Spy Who Flashed Me. I had a different title and I was told to make it more exciting, so this is what I came up with. I don't know if it's very relevant, but you can decide. So we were talking today about exploring and defeating physical access control systems. This is my first Insomnia hack, my first time to Geneva. I'm very excited to be here, so please excuse any anxiety. It's mostly excitement. So who am I? My name is Michael. I am a researcher at Orange Cyber Defense in South Africa, which is the same thing as Orange Cyber Defense Switzerland, but in South Africa. Primarily, I do research and then penetration testing. It's sort of a combination of the two, but we have a sort of a focus on the research side of things. We're always looking at interesting assessments that have good prospects for research work and developing tooling and techniques and interesting stuff to kind of stay ahead of the curve. I studied electronics engineering and somehow ended up in sort of IT, DevOps side of things. And I've always had an interest in cybersecurity. I've been involved in the community, organizing conferences, participating in meetups, and just being generally a part of things for the last 10 years in South Africa. We have a very tight-knit cybersecurity community, and it's been really nice to be a part of that. I am on social media, but I don't do a lot there. I'm also not on LinkedIn, which a lot of people shout at me about, but I like my job, so I don't know what the point of LinkedIn is. Right, so what is this talk actually about? There are a few themes that I sort of observed. The one is that physical security and cybersecurity are both security, but there is often a disconnect, especially in South Africa where I'm from. Cybersecurity is, we know what that is. Physical security has traditionally been locks and chains and physical control measures, people with crowbars and explosives and that kind of thing. And that is still largely the case. It is still a lot of what at least South African physical security is geared for. But it is becoming an increasingly complex technical field. There are many more gadgets and access control systems that make access control better and give us more visibility and control, but they are not, they're affected by cybersecurity things much like anything else, but the people who implement them are not aware of those issues, really. They kind of just buy a thing that says it will do what it will do on the box, they trust it, they put it in, and as long as it functions as expected, they are happy. So that is what I want to talk about. A specific device that I noticed that made me ask some questions about its security and its integrity, and whether it would always work as behaved or if we could influence in some way. This is the device. You may have seen them. I have seen very few of them in Switzerland, disappointingly, because I've been looking for opportunities to have a recorded demo that I got while I was here. But unfortunately, so far, so good, I suppose, for you. It is a touchless sensor, and the concept is it essentially replaces a button. You wave your hand over it, and it triggers a relay to open a door. Yeah, they are found in all kinds of places. I mean, literally everywhere you would find a button. They're especially beneficial in places where contamination is a concern. So COVID-19 sort of accelerated that, the adoption of that, because people were very into not touching stuff. So this was quite popular. They also don't suffer from the mechanical wear of buttons, which is nice. They will eventually break, but they are relatively cheap and quite a convenient measure. So they are all over the place. You can flush toilets with them, switch on taps. They look different, they present differently, they can be built into different things, but they all function the same way. So the principle of operation kind of applies to every case that you would find them. So the one that I focused on was a specific use case of access control. Very common thing, you are allowed to go into an area if you have access. So authorization is through biometrics or some kind of RFID thing, and then the door will open and you can walk through. But then to come out, you shouldn't need to authenticate to leave in a lot of cases. This is also impacted by fire code because you need to be unimpeded. If the office where your access card is burning down, you shouldn't need to have to go into the flames to fetch it to let yourself out of the area that's on fire. So there are obviously rules and regulations that vary by country that mandate that you should be able to leave without authenticating. So that's implemented in different ways. Traditionally, it's just been a button or something like that, a push bar. Sometimes there are those green sort of emergency exit things, sometimes a combination of them. What I noticed about these devices is that they looked just as cheap as the ones that were used for flushing toilets or opening booms or issuing parking tickets. They didn't look more secure or any better. They looked cheap, and that usually doesn't imply great security. So I started asking questions about how does this work and how could we make it work in a different way. The door doesn't care which way you're going. The door opens and it's passage, so you can move in either direction. So if you were able to trigger the device on the other side that didn't need biometrics, then you could walk through into the protected area and you could continue with whatever malicious thing you wanted to do. So I wanted to know how it worked. Thankfully, like I said, it was inexpensive. I had a look at Amazon. I found one for 13 francs. So they really are not expensive. You can buy these things just about anywhere. There are so many different variations of them. Almost none of them have any branding on them. There's one major company that makes a version of this that I'd like to get my hands on. Those ones are not inexpensive, but they are cheap. So I just purchased one so that I could open it up and I could investigate it further, because it's not always great to open up your client's access control systems. Sometimes, but usually not. So the first thing is sort of the principle of operation. How does this work? How do you detect that a hand or a reflective surface is close to the sensor? There are a couple of ways. So I can say, having done this with sensors and stuff, there are 3 examples. There are more. The one is capacitive touch. That would require a very close proximity. Usually capacitive is physical contact, but it can work from a very short distance. The problem is that these tend to trigger from anywhere from 2 to 10 centimeters, sometimes even more. So capacitive is out. Ultrasonic is possible, would function and look much the same as a parking distance sensor for a vehicle, but that use case is more focused towards measuring the actual distance. So while that would work, it seems needlessly complex. And because these devices are cheap, the third option, which is infrared, is the most likely and turned out to be the way it was implemented. And the way that it works is that it emits a signal, and that signal gets reflected off a surface. The thing that's quite telling about this, before even opening it up, is you'll see this. Generally, that sensor looks almost black, but if you shine a light on it, there's a sort of semi-transparent red plastic, and that is very common for infrared applications. So you'll see this in TVs. You'll flip a 0, the little plastic thing. It's all going to be that color because it conceals the electronics inside, which look ugly, but it allows infrared to pass through relatively unimpeded. So it's a very good hint that infrared is in use, literally just that kind of a plastic with that color and that opacity. So opening it up, excuse the flux on the board. A lot of that is my doing. I got my soldering iron out before my camera, which is usually the case. But this is more or less stock standard. I hadn't really changed anything here. So yeah, that's what it looks like. It doesn't look like an expensive device. I mean, I can't tell you, I could probably tell you why, but you look at it and no one goes, oh, well, that must cost 300 euro. It doesn't. So breaking it down into the internal components, I won't go into the details. It's not very important, but basically there's a few things here. In the middle, the green box is the emitting LED that transmits the signal. The blue box is the receiving one that receives the signal. So those two are sort of the main components for detecting that. There's LEDs all around in the purple boxes, and then the orange box is the only thing that is not on the top right. It's the only one that is not sort of off the shelf. I couldn't just buy it anyway. And that is the controller that passes the signals and decides whether reflection has been detected, and then triggers the relay, which is the top red box, and then effectively your door opens. So that's what's inside. There's nothing too exciting or complicated. And then on the other side is a adjustment for range. And I say range specifically because a lot of the time it's marked as sensitivity. But through tracing how it is connected to the circuit and how it works, I determined that all it is doing, and it's a valid thing to be doing, is adjusting the brightness of the emitting LED. So the amount of light that's emitted varies, but what that implies is that our sensitivity on the receiver is constant. And that is something we're going to dig into a bit later, but it is an important point on this. And then in the front, it essentially has a shroud, so you can see the plastic housing. It stops the sensors from picking each other up by virtue of being next to each other. So the idea is to pick up something that is, perpendicular to the sensors, not, detecting their own emissions without a reflection. And that's all there is. That's the entire thing. So my first thought was, well, it triggers from this far away. What if we could trigger it from further away? Often it is on the opposite side to a biometric or whatever, so you can't actually see the sensor. But in those cases, I'm interested because glass doors are quite a common thing. That is something that comes in very important. Glass doors are kind of important for this talk. Anyway, so sometimes they are opposites, the sensor and the biometrics, and you can't see the sensor, but sometimes due to space constraints or just implementation, they're on the wall on the side. And so in that case, I thought, well, how far away can we make this thing trigger from? So I set it up for, I adjusted the knob until it triggered at 10 centimeters with my hand as a sort of nominal value. And then I started playing with mirrors. That is a photograph of a mirror. I'm sorry it's not clearer, but you can see my hand and my phone. Mirrors are hard to photograph. They just show you what you're taking the picture with. So I did some tests. I used a normal mirror. I lined it up. It was quite tricky. And I got 6 times the nominal range, so 60 centimeters. Obviously, that would change depending on the sensitivity of the sensor. And then I used a concave mirror, and which essentially the beam, the light rays, particles, they converge at a point depending on the curve of the mirror. And the range, it's a bit of a cheat because the range is kind of determined by that convergence point. But I got 20 times the range of nominal, which is 2 meters. So this is looking like it could be something, but it turns out it was a complete waste of time. The few reasons is, one, we don't control the emission, and very often it's not sent to 10 centimeters. And if it's sent to effectively 5, then our range is 1 meter, which is not a lot. The other thing is it only works with line of sight, and very specific line of sight. Because of the shroud, you have to be exactly perpendicular to it, within a few degrees. There is not a lot of tolerance. So even if it's on the side and the door is here, shining something or holding a mirror at this angle is not going to trigger the sensor because it has to be here, which implies you're already in the safe space. I've never seen it implemented where the sensor is facing out into the unsafe space, which is a good thing, I suppose. Somebody has thought about this. So mirrors were a waste of time. So we moved on. The other problem is if you're trying to reflect off something, this is a wall, a picture of a wall. You'll notice you can't see my phone or my hand in this picture because walls are not reflective in the same way that mirrors are. So if for some reason we want to try and bounce the light, again, we don't control the emission. If it's too weak, it's not even going to bounce off the wall, and we can't, it's just not actually feasible to use the device and try and use its own signals. So that was the initial sort of thing I did, and it's not a good hypothesis. So the next thing was to sort of look internally. How does this thing actually function? What is it doing? What is it looking for? What does it trigger on? So I put a logic analyzer. If you haven't worked with electronics before and you are even vaguely interested, look at getting one of these. They are very cheap, and they give you a lot of insight into stuff. And because they are cheap, you can break it, and you can buy another one. Buy 2 when you buy the first one, save on shipping. Very useful. Between this and a multimeter, you can do most things. There are lots of very fancy, very expensive things you can buy, but I would put that on the top of the list. So, nominal operation. We have, this is what the logic analyzer looks like. The output from the logic analyzer. So we'll go to here, to the beginning. So the top box is the emitter. This is the LED that is transmitting the signal. And we can see that it sends a signal every so often. I don't know what the period of that is, but it's 30 milliseconds in the gap, so call it 15 milliseconds of signal. It's very quick. This happens many times a second. The second box, the second signal is the receiver, so what it's detecting. And the third one is the relay state. So what we want to see is this changing from low to high, and this line will literally just jump to the top. You'll see the transition, and that means that it's picked up a it's detected its own signal, and the relay has triggered, and the door is opening. So this is really what we're looking for. So it does this forever, looking for some sort of signal, and you'll see at this point the receiver is starting to pick up the signal. Sort of as you move your hand closer to it, the reflections will get stronger, and you will see more of the signal being detected by the receiver. Because of the time scale, it happens quite slowly as looking at this. But it picks up the first one, and the second one, it's stronger, but you can see it's not a consistent pattern. And this is changing the way it's emitting the signal as it detects the pattern. And on the third one, you can see this looks perfect. The bottom is a perfect representation of the top, so it's receiving the signal that it's emitting, and at the end, the relay triggers high. And that means the door's open. So now our hand is close enough for it to pick up its own signal. Great stuff. This is how it works. We have two questions about this, two things that I noticed looking at this. The one is that the emitted signal and the received signal, I've said they look the same. They don't really look the same. For one, it's inverted. The other thing is you'll notice this is a solid block. This is a solid block. The emitted signal is not. And if you zoom in, you see that's because it's a frequency. The other thing is, despite our hand being right by the sensor, there is a delay between this emission and this happening. So the received signal sort of lags the emitted signal, and that's an important detail that, of course, we want to answer that question. So why is there a frequency in the emitted signal and a solid pulse on the received signal? If it's a dumb emitter and a dumb receiver just talking to each other, you'd expect to see the same thing. It would sort of couple when your hand is there, and you would just get a duplicate of the signal. And the other thing is, why is there a delay? The answer, I'm going to give you away the answer, is that the receiver is not so dumb. It turns out the receiver is actually quite a complicated piece of hardware. It looks awful, and they are very cheap. But infrared communication is a problem that has been solved many, many years ago. You may know about TVs when the invention of TV was a thing with remote control, so you didn't have to get off the couch. That was a wonderful invention. Initially, I think they had cables. There were versions that had sort of ultrasonic. Eventually, they settled on infrared, and with the exception of Bluetooth with a lot of the smarter TVs, that's still the standard today for communicating with devices cheaply. So this infrared receiver does quite a lot of things. Because it's present in so many different places, it's a big enough problem to solve at a mass scale, and so these things have been devised to do a bunch of stuff. So we'll get into that. But the supply and demand has turned this into a cheap, easily accessible component that does lots of stuff. So this is a block diagram of what's inside the infrared receiver. This is not an electronics course, so I'm just going to say there's a lot of stuff in the box. And what that implies, and we'll look at the details now, is that there's stuff happening between the signal entering and the signal leaving. And there's an amount of sort of confirmation and checking that the signal is correct, which introduces processing delay. And this is good for us. So if we look at the next page of the data sheet, this isn't the data sheet for the exact model. Like most no-name brand products, most of the components don't have any markings on them either. So this is an equivalent thing, but they all work more or less the same way. The first part circled is essentially saying that between 7 and 15 cycles need to be detected in order for the receiver to confirm that it has picked something up. And then you can see the two vertical lines on the left. That is our delay time. That's what we were seeing in our capture, the lag between the input and the output. So this is interesting for a few reasons. The one is, this is explaining why the emitter is emitting a frequency. This is how these things work. The receivers filter on a specific frequency, often 38 kilohertz for remote control systems. The touchless sensors, some of them are 30 kilohertz, some of them are 38. They vary. It can be, you can decide which one you want to use. But the reason for having a frequency in the first place is that infrared occurs naturally. If you take a device that just measures the amount of infrared it's detecting, it's all over the place, depending on if the sun is shining or other devices in the room. Fluorescent lights are apparently quite a big problem for them. So introducing a specific frequency, that's something that won't just occur in the wild. And this is very good for things like touchless sensors because it confirms that you're picking up what you're expecting to. You're not just picking up some spurious infrared emissions from something else. So yeah, this is interesting. The main thing here is that between 7 and 15, that's not a constant number. That's a variable thing, which implies that we have some tolerance. So the receiver demodulates the carrier, and that's why we see a solid pulse as a result of the carrier frequency. And then, of course, the 7 to 15 cycles is not consistent. So if you take 15 cycles at a 30 kilohertz frequency, that's half a millisecond or 500 microseconds of tolerance that exists. So this is where we start to fuzz the device and to try and introduce our own signal to see if we can trigger something, because we can't rely on the weak signal that it is emitting. So this is my first prototype. I didn't bring it with me. I don't know if I would have made it through border control if I had. So I left it at home. It has a laser on the side because you can't aim infrared visually, a lens with different slots so you can change the sort of focal point, and then a very powerful infrared LED at the back. So that's what I built to start experimenting with these sensors. So now we go back to the logic analyzer, to that. And we see the first is, I've left out the the top one is the attacker signal. This is the signal I am generating. The bottom one, or the second one, is the emitter, so what it's generating, but I'm nowhere near the device, so there's no reflections coming from it. Everything the receiver picks up, which is the third one, is from my external signal, and then, of course, we have the door open signal at the bottom again. So when that goes high, then it's a success. And you'll see I tried to copy the signal that it was emitting fairly closely, but I didn't try very hard to make it exact. As you go along, you will see that the two sort of drift together and start to get closer. At this point, I don't think I was shining the torch directly, my light directly at the receiver, so nothing was being detected. But if you carry on, you'll see now it's lined up, and my attacker signal correlates with my received signal. So now we are influencing the device. We've got confirmation that we actually have some control, and we can do something here. So we wait for it to sort of drift into phase, and what I start noticing is that as soon as there's an intersection, the emitted signal changes, and the more that it intersects, every time it intersects, it changes to this pattern, and this is not good. As you'll see, the relay signal never changes in this whole capture. There's a lot of shining lights and swearing, and this ultimately didn't work, which was obviously not a great result. So, and I really thought it would, which is why I got sad. Everything I'd seen made me think this is a very simple, dumb device. It's cheap. No one tried to make it secure. If I just emit the signal, it will open the door, and then we can be done with this. But I followed so many rabbit holes. I shaved so many yaks. I spent so much time building things that were helpful, but were ultimately unimportant. And I kind of just tired myself out with the project. And when I got to this point, I went, it should have worked. It didn't work. And then I kind of got over it and I stopped for a while. And a few months later, I was speaking to somebody and they didn't understand electronics very well, which meant they were asking me some questions that didn't make a lot of sense. But in that conversation, there are some questions that I don't know if, I mean, they didn't know what the answer would be. It wasn't a rhetorical question, but they got me thinking about alternative approaches and sort of engaging with people and sort of talking to community about what I'd done so far. People made some suggestions, and I kind of got inspiration to pick it up again. And so I started looking at it a little while later. So my assumption, and this was the biggest mistake I made in this whole project, was that assuming that this changing of signal was a security feature. Because it looked like a security feature. Of course, you're going to change things to, if you're in control of the emission, you can change the emission and you will get a different signal back. If you have an external interference, then you have no control over it. So if you change your emitted signal, your received signal won't change, and you know that it's not real. So this is what I thought was happening, and this is why I got so demotivated. But in reality, this is designed for reliability, not for security. Nothing about it suggested it should have been secure. So this was a bad assumption on my part. And there was a bit of confirmation bias, because this is what I looked at it, I went, oh, it's security, and now I'm done. So it's just a little thing with research. I'm quite new to research in general, but I really enjoy it. And it's a lesson I learned was to prioritize proving or disproving theories as quickly as possible, and then continuing. If you think something is the case, make sure that that is actually correct before it makes you change the course of your research or stop what you're doing. So that ultimately led to me picking it up again and continuing. So now we are trying again. What we have established is there are two keys to the puzzle: the center frequency and the pattern. And before I was thinking, well, how do I detect when the emitted signal is changed so that I can respond in relation? I can't. The emitted signal is too weak. I don't know how this is supposed to happen. I thought very tight lenses and some photo transistors, but it just wasn't really practical. But turns out that didn't really matter either. There are only two things that mattered. It was the carrier frequency and the pattern, so the timing of the emitted signal. And there are two things in our favor. The one is because of the receiver only changing the emitted signal strength, our sensitivity is always 100%. Those devices that receive are you've used TV remotes. They work if it's in the general vicinity of the room for the most part. And it's the same hardware we're dealing with here. The other thing is that there's variable tolerance. There's 500 microseconds of sort of timing grace we have because the device has to allow for it. Otherwise, it might not work. So instead of getting fancy and trying to react, we just start at the beginning with emitting that secondary signal that it emitted. Thinking back to that seems very obvious. I don't know why I didn't just immediately do that, but we're always much smarter in hindsight. So first thing was to obviously measure the timing. The carrier frequency we know is 30 kilohertz, and the timing is there. The numbers don't matter too much, but on this particular sensor, roughly 690 microseconds on, and then 517 off. So we try that. Let's not emit the first signal. Let's not emit a big pulse. Let's just do this and throw this at the sensor and see what happens. So I don't want to rename it. I want to go there. Right. So emitted signal. Where are we? This is the compromise between doing a live demo and having a physical logic analyzer attached to a live device. I thought this would be easier. Okay, so we start here. The sensor is emitting the signal like we expect it to, a solid signal every 50 milliseconds or so. Then we introduce our signal. And immediately, as soon as it picks up that there's anything, it changes the pattern. So remember, this block has to correlate with this. At the moment, it's too far away. I'm using sort of timing drift to my advantage here, because at some point, these should get close enough that it will look like it's receiving its own signal. So we do it a few times, and then see, I'm emitting for far longer than a single thing, because I wanted to make sure that I intersected with one of them, and it turned out it didn't mind that. It wasn't a problem. So here we start getting a little closer, and by here we are, if you look at this timing delay, between when the emitted signal is emitted and my signal is received, it is, where is this? Okay, I can't figure out how to get these details again. But it is essentially 10 pulses. And that is within spec. That's between the sort of 7 and 15 that we want. And if we zoom out, we notice at this point, with this test, the device picks up that it has received a signal, that it emitted, which is not true, and the relay switches and the door opens. So this is with no reflections, just introducing an external signal. So this actually worked with this particular sensor. So we'll go back to this. So now I was a happy Pepe, and everything was great. So I then, of course, that was not the only sensor. It was one of the more common ones I saw, but I had a look at some other sensors. There were 4 that I've tested so far. It turns out this was the second most secure of them, which is not a great result. 2 were a lot worse. They didn't change their signal at all. They just emitted something, and if they received a signal, then they switched. And the one I have yet to defeat. So I'm still working on the 4th one, because for some reason it just seems to not react to my signal at all. The receiver picks it up, and the chip, obviously the tolerances are tighter or something. So now we have a working attack in theory. In practice, we still have this. And I don't know who's done a red team. I don't know if you think that this would be a good thing to have. To note, it's not the full picture. It's on a tripod, so it sits this high. It doesn't really fit in a pocket or a backpack, and it's not a great option unless you say you're a new kind of quantity surveyor who has, I don't know. It just seems not like a good idea. So I'm going to ask is some audience participation. Can anybody guess what is portable, has a battery, and shines light at stuff? This is very easy. It's not a trick question. Anybody? A torch. Yes, congratulations. You win the prize. So this is a very easy place to start for building an attack that's actually portable. You can. It sort of has a plausible deniability, but it's a good platform for something like this. So that is what I ended up looking at. I bought a couple of torches. This ended up being the one that checked all my boxes. It needed space for additional components. It needed to be easy to modify and not expensive, because at this point I was paying for it myself, and I didn't want to pay many thousands of rands for a torch that I was going to break anyway. So this particular one worked quite well. And if you open it up, this is the sort of internal of it. And at the bottom, this is an unmodified torch. This is exactly how you buy it. There's a PC board that has a couple of capacitors, resistors, a little chip that changes the brightness of it every time you switch it on and off. And then an LED at the top, which is about a little bit thicker than that PC board. But in between the LED and that PC board, there's just empty space and 2 wires, which was fantastic. So this seemed like a really good option, and it turns out it was. So I made an initial prototype. There was a lot of insulation tape that I had to take off to take this photo, but I kind of just soldered everything together, insulated it, and shoved it in there so that it would be inside. So that was the first prototype. It wasn't great, but it did work. And then what was really nice is the LED that was used on that torch is a standard form factor. So that LED in the picture is an infrared LED, which is obviously relevant to our attack. So looking at the PC board itself, that is, again, unmodified, but what I noticed is there were these two terminals where power would be available. Some small modification would be required, but ultimately I'd be able to get power from there. So the idea was to build a little PC board that would sit perpendicular to that and be soldered onto those 2 points, and there would be lots of space inside for it to work. So that prompted me to build my first PC board. Sorry, I've rotated the image so the text is upside down, but the idea is to show you those are the points in the blue rectangles that would be soldered to the board at the bottom. And so I got it ordered, made it, assembled everything on there, and it was surprisingly inexpensive and surprisingly easy to do. So I just put a little thing at the top there. There's no affiliation or anything, but it's a course that I went through to sort of figure out how to make PC boards with open source software called KiCad. So if any of you are interested in it, like, it's worth doing, and it's cheaper and easier than you probably think it is. So yeah, if you're interested, that's a really great resource to figure out how to do this. I was always scared it was going to be too expensive or it wasn't going to work, and yeah, it just isn't actually that difficult to build simple stuff. And that's what the end result looks like. So it's soldered on alternating sides, so you can't see the solder on the left, but it's attached to the board, and it's, yeah, it fits perfectly inside the torch. That is what it looks like, sort of exploded view. And so now we have a red team tool, which is great. And in South Africa, this is something that, I mean, it is implemented in the wild like this. So I've been quite keen to play. So I have a demo rig. It is over here. I will show you. So there are 4 sensors in the front here. If you can't see, it's not the end of the world. This switch just enables light to come on the side so that it's obvious that something is happening. But if you move your hand towards the sensor, the light comes on. There's 4 of them. They all have different patterns and different frequencies, but all of them activate if you put your hand close to it. So for the sake of the demo, I will put that over there. So the lights are facing you. And then if I take this out, another nice feature is that it has a telescopic zoom. It's not very easy to see, but essentially you can change how focused the light is. So if I switch this on, nothing happens because this is just a regular torch. But you can see if I focus the beam, if you can see the white sheet, or maybe I can do it on the screen, you can change, you know, if you want range or if you want it to be sort of a wide beam. So this is the torch that I based it off. The real one, the fun one, is in my pocket because it fits there now. It doesn't need to go in its own suitcase. And if you shine it at the sensors, you'll see they almost immediately trigger. That first one sort of starts, the second from the top one is a little bit, it tends to start ignoring signals if you do it too much. So if you kind of take it away. But again, this is, okay, so I've triggered 3 of the 4 sensors. I can't trigger the 4th one because I haven't figured out how. But don't clap yet. This is not practical. If you walk up to a glass door, in principle, there is biometrics here, and on the other side of the door is this, not facing you. That's not how this works. It's facing away. We do this. So to sort of simulate a more realistic attack scenario, we have a divider with a white sheet on it. And if you take the torch, I can actually stand quite far away. You can trigger it by bouncing it off a surface. I was waiting for that 3rd one to come on. Anyway, so that is the practical attack. This can now actually be used in engagements. So far, the only people who have implemented it are the people who are too cheap to pay for an assessment. So I I have successfully gotten into office buildings, I've gotten into an apartment block, I've gotten into a library, I've set off a soap dispenser and dispensed soap onto the floor. That was unintentional. I was trying to open a door. But it works. It's compact, it's light, and if somebody asks me what it is, which somebody has done at an airport, I say it's a torch, but it doesn't work. that's So line of sight range is a factor. It can do, I've tested it up to 100 meters, and I've managed to trigger a sensor from 100 meters away. In some scenarios, you can use that. Maybe the entrance that you're trying to get into faces onto an external window, and you can shine it through there, and your partner can come in through the door. There are ways to use it like that. But in a practical attack scenario, the reason I made it so powerful is so that we could bounce it off semi-reflective surfaces. And there's one particular sensor in there which is just insanely sensitive. But even from this distance, I can get... A third one's not playing with me today, but... Yeah, the range is now something that is actually practical. This is something you can do with a flipper zero as well. I figured out the timing and sort of moved that onto a flipper zero, and that does work. But the range is severely impacted, and so the practical usefulness is limited. I wanted something that we could actually use in engagements. So the next thing is interrogating new targets. So, like I said, there are so many variants of these. The office building I broke into, I got through every entrance that they had, the basement, the first floor, the second floor, into the secure area where the development team was with permission. And then I got to the data center, which before I went in there, I thought, this is my goal. I want to go to the data center. And I shone my torch at that thing for so long. It looked exactly the same as the ones in the rest of the building. Eventually, somebody let me into the data center. I shone it directly at the sensor, and nothing happened. And I realized that this is a different internal, different frequency or different pattern, or whatever it was, my attack didn't work. So for new attacks, new sensors, to add them to the torch, we want to be able to get the signal and to see what we need to emulate. It's not always practical to physically connect. The ideal is to put a logic analyzer on like we did before. But again, in a client engagement, not the best idea. So we need a way to capture signals. The problem is we could get a receiver and have it on the outside, but the receivers demodulate the carrier frequency. So they essentially throw that data away. And that was the first key to getting this to work. You could guess the carrier frequency, or you could change the carrier frequency, but of course it's better if we just know. So I found a very obscure part. The standard ones that are tuned to a carrier frequency, they are so readily available. This I had to special order. But essentially it's the same thing. The difference is it actually it doesn't filter the carrier out. So it's the perfect device to use to hold up against a sensor and to capture that signal that you can use to develop an attack. Because the devices respond in different ways, it's quite difficult to make an attack that you know will work. It's kind of a feedback loop, but this data is kind of where you start with that. So that's worked quite well to add additional sensors without opening them. The big white rectangular one, that one is outdoor rated, so the whole thing is encased in resin. I can't put a logic analyzer on it. So that was the only option in that case. So this is obviously a problem. It's not great that we can open doors from the wrong side and let ourselves in. And the reality is, because these are just mass-produced, no-name brand devices, we can't just go, hey, manufacturer X, please fix this. Because there's manufacturer A through Z and then more. So, and we don't know who they are. You could argue we could find them, but I think the best way to sort of solve this is an awareness thing. For people who implement them, they should be convenience buttons, not security barriers. They should never let you into a space that you should not be able to get into. There's things like having opaque doors. The glass doors are what make this possible. A lot of the time. But if you have an opaque door, and if you're a motivated attacker, you drill a small hole in the door. It doesn't take a lot of time or effort. Yes, it's hard to hide, and you probably can't do this in a red team exercise, but a motivated attacker with a lot of nice stuff on the other side of the door, they will do this. So they shouldn't be placed in sensitive areas, and essentially beyond flushing toilets and dispensing soap and maybe opening a door that anybody should have access to, they shouldn't be used for security. For manufacturers, if we think technically how could we make these sensors more resistant to external interference, well, you'll see a lot of the signals they sent were when it was not transmitting. A very simple thing which would make these much more resistant to attack is to stop processing for 5 seconds if you detect a signal that looks like yours when you're not emitting one. The other option is to have a random pattern, and with reasonably tight tolerances and ignoring false positive signals, you could get quite a secure device which would work quite well. So there are 2 things I want to sort of take from this. The one is for physical access control. Again, it's an increasingly technical area, so look for devices that look cheap. I'm sure you've opened a web app where you go, this thing has SQL injection. I don't know how I know this, but I can just see. It was designed on Microsoft front page 97, and it's clearly got SQLi. So it's the same with hardware, and the cost of the hardware also determines how much effort is put into making them secure. So it's something I've been trying to look at. I haven't found any fun targets yet, but I'm looking out for things that are cheap. And the other one is just sort of a quick comment on research. A lot of projects, this ended up not being very technically complex, but when you are doing your own research, your project is the thing you're focusing on. Your project builds on years of experience and knowledge that you've built up through your career or your hobby, if that's what you did. And when other people look at your project, they see the sum total of that. They don't just see this little, weekend project that you built on top of what you've already done. And all of the stuff and you've experienced is also built on tooling and things that other people have built. We stand on the shoulders of giants, and we should strive to embrace that and not to say, oh, we only did a little bit of work, or my research isn't good enough. And where this gets really valuable is when we have collaboration between people. So when you start building on each other's stuff. So somebody with capability you might not have will develop something, and you could build on top of that, and you end up bouncing off each other, having ideas, encouraging each other, and it's why I think that the community is so important. Conferences like this, the engagement we have is really valuable, and we should do more of it. We actually have a slogan for this year, make PRs, not war, inside our Cyber Defense South Africa team. And the idea is to try and focus more on contributing than consuming. So I just want to encourage, if you see something, you go, oh, this bug exists in this common project and it's easy to fix, because you have the knowledge and experience to realize that, make the pull request, submit it, contribute. You do a little project, stick it on GitHub. Somebody is eventually going to search for that exact string, and it's going to help them with their own research. And you will do the same at some point. So be kind to each other, encourage each other, and contribute. And that is it. Thank you very much. I don't know if we have time for 1 or 2 questions.
Yeah, I think one.
There's one here.
In Switzerland, we most often have the sensors above the doors which detect when you get near them. Have you looked at them?
I have not looked at them. I mean, I've looked at them, but I haven't looked at them. They're quite expensive. They work on a different principle. I think they are sort of microwave-based. There was Deviant Ollam figured out that you could trigger those by using compressed air inverted and spray it through a gap in the door, or getting paper or some other object through. And so there were some attacks like that. I haven't looked at sort of external signals, but I think it's a bit more complicated. But it is on my radar. I would like to look at them at some point.
So thanks. And I think if you have any questions, so you can just come in.
I will be here all day, and Shifty Mike on social media. Thank you very much.
Okay.